Good morning, everyone. If you can take a seat, if you don't mind. All right, so I'm Daniel Prodell. I'm the co-chair of this conference and an emeritus professor at The Ohio State University. And since 3 weeks ago, a local resident here in Southern California. Putting up or organizing a conference is really a team effort. And during the last 3 years, I was reminded on a weekly basis, what a wonderful community we are all part of. Whether it's at the local level with the Los Angeles section or Cal Geo or the Orange County section, whether it's at the national level with an army of volunteers, it would take me a whole hour to properly thank everyone. Whether it's the Johns, the Jays, the Teams, the Garas, the Stephans, the Chris, the Nevins, the Travis, and I could go on and on and on, but I'm not going to do it. It was a ride in the rental car. Professor Tim Stark and I, in 2017, we were in the state of Washington looking at a several million cubic yard landslide. And on the way back, we were discussing ways in which the Embankment Dams and Slope Committee could help organize events, coordinate things. And that was what ended up being the seed for the 2021 Geo-Extreme conference. One of the things during that ride that I remember is how much of our practice these days is being governed or influenced by extreme events. We're moving away from just doing designs, but kind of trying to forecast how earthquakes, hurricanes, and many of these events, shape the work that we do. This year alone, we were reminded by the wildfires here in Los Angeles, the devastating floods that affected Texas Hill Country, tornadoes in North Dakota, and internationally, just recently by Hurricane Melissa, the floods that affected Pakistan, the devastating earthquake in Myanmar, and I could go on and on and on. But I wanted to bring somebody very special. He's been absolutely a fantastic co-chair during the years, and he's really the brain of the operation over here, Dr. Navid Jafari. Thank you very much, everyone.
Good morning, ladies and gentlemen. It's a pleasure to be here, and thank you for being here. I am an associate professor in the Zachary Department of Civil and Environmental Engineering at Texas A&M. And as Daniel said, we're co-chairing this conference. And what we wanted to really capture was the essence of the 2021 conference, which was held in Savannah, Georgia. And that was highlighting key natural hazards and having great discussions about them. And in 2021, we were able to have a lot of input from the federal government, whether that was NOAA, NASA, USGS, Army Corps of Engineers. So those of you from the federal government who could make the conference this week, we really thank you, but we also just want to acknowledge all the federal employees, the researchers, the engineers, the scientists who help us in the extreme event space or the hazard space. We have a lot of different hazards in this conference. I would say in 2021, we were piggybacking off a lot of the hurricanes. We certainly have had our share of hurricanes since 2021. Wildfires has increased in our visibility, and we did not plan when we chose Long Beach for the wildfires of January 2025. But this wouldn't be a hazards conference if we didn't start with a little bit of seismic, and since we are in California and Southern California. And so the first plenary session that we'll have for this conference will be seismic site response, and I'd like to invite Professor Jon Stewart from the University of California, Los Angeles to lead that session.
Thank you, Naveed. And let me just take care of first things first. How about that World Series, huh? Got any Dodgers fans out there? That game 6 and 7 was as good as baseball gets. So if you're a baseball fan, you were in heaven those 2 days. I'm going to go and take the hat off now out of respect to our Canadian colleagues. So it's a great pleasure to be with you as a fellow Southern Californian, to welcome you here to our beautiful part of the world. And indeed, earthquakes are a really major driver of our risk here. And so it's fitting that we start with that. If we can pull up the next slide. Oh, I guess I do that. All right. So this is the outline of our session. You see it's called Seismic Site Response, and then I say NGA West 3. So NGA is Next Generation Attenuation. It's a series of projects going back over about 20 years now. There's been projects in the West, projects in subduction zones, projects in the eastern part of the U.S. In the West, though, we've done 3 iterations just because the amount of data and the amount of knowledge is continually evolving at a very rapid pace. We get a lot of data here, and we learn from it. So we're going to be focusing on the site response part of that in particular here today. We have 3 presentations followed by a panel discussion. So that's the way we've organized it. Each of the 3 presentations is 25 minutes. I will be doing the first one, and I'll be talking about kind of regional and sub-regional issues as it relates to ground motion modeling, but in particular in site response. Then we're going to hear from Dr. Laurie Baise, Tufts University. She'll be talking about a different way of conditioning site response models through the use of geospatial parameters, which is an innovation that she and her team have brought into the project. And then Professor Youssef Hashash from the University of Illinois will be talking about simulations that his team has run in order to constrain the nonlinear part of the site response models using the conditions here in the western part of the country. And then we'll get to the panel discussion. All right, so we'll start with my remarks here. You can see the title, NGA West 3 Ground Motion and Site Response Modeling at Global and Regional Scales. So what I'm going to be doing is going through these 4 items in the agenda. So I'll have a little bit of a substantive introduction. In this introduction, I'm going to talk about what are the components of ground motion models and how can we view them from both a global and then a regional perspective. I'll then take a bit of a deep dive into the NGA West 3 database, which has been recently completed and is available. So we'll talk a little bit about the characteristics of that database with an emphasis on site parameters. Then I'll go through this topic of site sub-regionalization. I'll explain what that term sub-regional means when we get there and why that's being considered as part of the project, and then I'll have some closing remarks. Okay, so just to get you oriented, for those of you who don't live in the ground motion world all the time, like some of us do, so we use a lot of acronyms, one of which is GMM, ground motion model. So just starting with that. And these GMMs do a couple of things. One is they give us a natural log mean of the ground motion conditioned on a series of parameters that come into the model. So we have these three terms here, which are predicting the term on the left, and that is the natural log mean of a ground motion intensity measure like PGA or spectral acceleration at a set of periods. All right, and so the first term on the right side, the FE, is the so-called event part of the model or the source part of the model. And so that's going to be a model conditioned on the earthquake magnitude, the style of faulting, the depth perhaps of the rupture, and things of that sort. If we look at what those terms typically give us, you're going to get ground motion on the y-axis versus, for example, magnitude on the x. We can fix at a certain distance and see what we find. And we'll usually see a trend something like this for the higher frequency parameters. That constant slope at the lower part is essentially baked into the definition of magnitude itself. The classic local or Richter magnitude is basically the log of ground motion is related to magnitude. Magnitude is defined that way. As we moved into the moment magnitude scales, that basic linear relationship persists. But then there is a saturation that occurs at larger magnitudes, which is something that we see with our larger events beyond about, say, magnitude 6 or so. Then we have the path part of the model. The path part of the model is conditioned on distance parameters. There are several of them. So one of them you'll see at the top, horizontal along the ground surface, RJB. That is the distance to the surface projection of the fault. The J is for joiner, the B is for bore. They are the researchers at the USGS who introduced this metric for us. Then you see R rep there, that's the distance to the surface, or to the projection, sorry. That is the distance to the fault plane itself without any surface projection. So the top figure is just showing that for a vertically dipping fault, and the bottom part is showing that for dipping faults, non-vertical. So if we look at this path part of the model, we can now fix the magnitude and see what we get. And you'll see a pattern like this, where the first part of the model is essentially showing saturation. So as you get very close to the fault, there's no longer any change in the average ground motion with distance. And there are terms in the model that account for that, the so-called H term that is added to distance that you see there. As we go a little further out, it transitions essentially into a log linear relationship, so log axes for both, and it becomes a linear relationship, which is controlled by the geometric spreading part. So the energy is essentially going out into space, it's occupying an ever-increasing volume, and that dictates a geometric reduction in the ground motion. And we go further out, so this would usually be in the western US beyond about 80 to 100 kilometers or so. There's a further attenuation off of that geometric spreading we call anelastic attenuation, which is energy dissipation within the crust. And then finally we have the site part of the model, and there's a number of different site parameters we use, but probably the most important of them is VS30, and I'm going to tell you a little bit about the VS30 parameter here. So we start with the VS profile and we consider the upper 30 meters. For those of you who work in this space, whether we start at 0 and go to 30, or whether we start at some other number and go to that number plus 30 has been a source of a lot of discussion. But the right answer here is unambiguous and very clear. You start at the surface and you go to 30, full stop, okay? So we look at that part of the profile. And any particular interval, we can measure, we have a velocity, we have a thickness, and we can take the travel time through that interval. We sum up those travel times, and that goes in the denominator. 30 divided by that sum of travel times is VS30, which gives weight to the slower layers. All right, so if this curve we looked at before, the distance attenuation is for a firm ground site, like a rock site, and then we add a soft soil site, we expect to see a pattern like this. If you go to the left side of that plot, you see that the line, the green line, is below the blue line. That's because there's nonlinearity. That's because the nonlinearity overwhelms the other factors, like impedance effects and so on, actually bringing the ground motion down where the shaking is intense near the fault. You go out to the right side of the plot, the green line is above the blue line, there's very little or no nonlinearity out there, and you have impedance and other effects that are bringing the ground motion up. So these are the kind of patterns we expect to see in our models. Okay, so now when we think about these models, starting from kind of a global scale, we have different types of earthquakes in different parts of the world. As I mentioned before, we have active regions like California. We have active regions that are dominated by subduction earthquakes, and we have stable continental regions, all right? So we have to have different models for those different regions because there are indeed distinct characteristics in the ground motion and those source path and source of path mainly, not so much the side effects varying between them. Okay, we're going to really be focusing here on the active tectonic region, okay? Now, when we talk about active tectonic regions, and we look at the 3 generations of NGA projects that we've had for these regions, there's really different scales in which the modeling has happened. And the first NGA project that concluded in 2008 was a truly global model. So we had data, of course, from California, but also Japan, Turkey, Taiwan were major contributors to this database, and we were essentially getting the global average in our models for those regions. We started to realize as we went into NGA West 2, and certainly in NGA West 3, that we needed to regionalize. And the regions are colored here on the map. You see, for example, Western North America, Japan, Taiwan, various areas in the Middle East, Greece, and Italy, and so on. Okay, so we'll talk a bit more about what that means to regionalize for those. If you look at the literature writ large, you also have what I call local models. That's a model that is created usually for a political boundary. It could be Italy, could be Greece, could be any number of places around the world where you limit the data you consider only to that region. Don't generally recommend doing that. It's too limiting, but we won't really talk about that further today. I'm just listing it for the sake of completeness. So what I'll take a few minutes to do now is talk about how this regionalization affects the patterns that we saw earlier. All right, and we're going to start with the path, which is one of the most classical ways we see these regional effects. And we see it in the anelastic attenuation mainly. So you can have some regions that have a more intact crust, and this more intact crust gives you less damping and a higher, we say that's a higher Q, a higher quality factor in the crust, and there's less attenuation of our high frequency parameters. Other areas have a low Q. They have even more than the average energy attenuation. And you see a few examples there in the text of regions where we've observed this kind of behavior. That VS30 effect that we see in the ground motion is also regionally variable. So here's an example of what strong scaling might look like if I have various indicators of site response versus VS30 on the horizontal axis. I fit a slope to that, and if that slope is a steep line, that indicates strong scaling. Some of the strongest scaling for VS30 is here in the western US, particularly at long periods. There are other areas that have relatively weak scaling with VS30. That doesn't mean they don't have significant site response, it just means that the site response is less correlated with VS30. And so that would be indicated by a flatter line here, and this is what we see in the eastern part of the United States. There are also regional effects with source, okay? And so one of those is where does this magnitude curve bend over? So Ken Campbell has done some work to look at this and shown it's a function of crustal properties that can be measured and considered in our models, particularly for subduction zones. A lot of studies have also been shown in different parts of the world that show that models may be systematically low or systematically high in different parts of the world. For example, Italy very often has lower than average ground motions in sort of a general sense, so you're just kind of shifting that curve downwards. Okay, so these are all regional effects that we see. So moving into the NGA West 3 project database next. I'm going to talk about the scope of the database and talk about the site metadata. I want to show a little love to Tristan Buckrice, who's here in the audience. Tristan was really the quarterback that made this team run and produce this database. He will be giving a talk later in this conference with more details on the database. This is the map, the global map that kind of highlights the different regions around the world where we collected data. And the main point I just want to make about this map now is Tristan and his team really were responsible for Western North America, which was a massive effort in its own right. Most of the other areas you see there have a local working group. So there was tremendous global collaboration on this, where there would be, for example, a group of seismologists and geotechnical engineers in Turkey, well, Italy or Turkey, any one of these, where they assemble that data and then they process it in a way that's compatible with all the other regions, and we integrate it into the database with, of course, due credit given to them for all of their efforts. So I'm going to step now through a series of slides that Tristan has put together that allow us to see how the database has evolved over the course of these different NGA projects and kind of what are the attributes of the database we have as of now. So if we start here, the plot that is on the left side is showing the number of records, and the horizontal is basically the project, which is different points in time. And the first one we see there is NGA West 1. Everything's kind of squeezed down near the bottom of the plot. I can't read it from here, but I recall it's about 3,500 records that we had in NGA West 1, which at the time we thought was, wow, truly extraordinary. We're so lucky to have 3,500 records. Little did we know that we would have a lot more in NGA West 2. That one, I think, is 21,000. If I squint, I can read it there. And you have colors there for different parts of the world. I forgot to mention NGA West 1, there's a lot of data from Taiwan and California. Those are probably the biggest contributors. We go to 2. California takes a much more leading role because we filled in, as you can see on the right side, we filled in a lot of lower magnitude events as part of that database. I'll explain later why we bothered doing that. As we go into NGA West 3, the western US has exploded again, but now it's not as large of a fraction of the overall due to really substantial data gathering campaigns in Japan, Taiwan, Turkey, Greece, and many others. Okay, so you can see here the huge growth. I think we're up to 175,000 records, and those are 3 components. So actually the number of records is 3 times that. And on the right side, you can see its distribution in magnitude, distance, space. Now, this is kind of an important plot because what it's showing for these different regions, on the left side would be Western US, and the top right is Iran and the Mediterranean, and then below that we have Taiwan and Japan. And what it's essentially doing is stepping from NGA West 2 to NGA West 3. So right now it's NGA West 2, now NGA West 3. Those lines that are on the page are lines drawn from the earthquake source to the sites that recorded the earthquake. When you see an area that has a lot of lines in it, it means we have a lot of sampling of the path, and where the sources are, we have a lot of sampling of the source within those regions. And it's pretty powerful to see that, of course, California is pretty well covered, better now than it was 11 years ago, but also Western US, we're really starting to fill that in. The basin and range area that's so important we're getting much better sampling there. And if you look in other parts of the world, I mean, my goodness, the change in the Mediterranean is really transformational. Not as big of a delta in Taiwan, but a big change in Japan as well. All right, and now here we're looking at kind of the overall database we end up with when we combine all of this together, different colors for West 2 and West 3. The basic point here is that we have a lot of data from about magnitude 4 to kind of getting towards the upper 7s. We don't have anything over 8. The earthquake in Turkey was a complete catastrophe, but we are learning from that earthquake. And one of the ways we're learning from that earthquake is due to the foresight of the Turks. They have a lot of instruments. There was a lot of great recordings of that earthquake at that upper end of the magnitude scale. On the right side, we see the number of records with oscillator period for response spectra. That fall off that you see beyond about period of 1 second is typical. This is due to the processing that we do of each record to only, to try to isolate as much as we can the signal and not be reporting out noise, okay? And so we want to use the signal part in our modeling. These plots are showing things broken down by region: Western US, Mediterranean, Japan, New Zealand, and Taiwan. I think the main point I would make here is we have very wide magnitude distance coverage in Western US, Mediterranean, and Japan. New Zealand and Taiwan, we were a little more targeted there at their larger earthquakes. The aim is to fill in the upper end of the magnitude range so we can get better magnitude scaling and similar effects. Our intent is not to create local models for New Zealand. They don't need our help. They can do that perfectly well themselves. Same with Taiwan. Now moving on to the site data. As I mentioned before, we have VS30 as our primary site parameter. We are getting VS30 from profiles, and we're getting it from what we call proxies estimates. The plot on the right is showing two things. It's showing little triangles where we have ground motion stations, and it's showing little colored dots where we have profiles. In each of these regional studies, including Western North America, a massive effort was done to compile as many VS profiles as we could from various sources, pair them with the stations so that we could make these linkages. And so we did that, and whenever we have a profile, of course, we use it. There are cases where we don't have profiles, still too many, and we use these so-called proxies. A lot of thought goes into these proxies. We try to use, we differentiate local, so proxies developed using information in a local area versus global ones. We look at different conditioning variables like the topographic gradient, surface geology, different things like that. We have hybrids of multiple parameters in the same model. We generally, where we can, use weighted combinations of models, particularly if the variables being used have some statistical independence, because that gives you a better outcome. And when we're estimating VS30, particularly in areas with not very much data to constrain the models, we provide epistemic uncertainties on the values. This is where we end up. This is basically showing you in yellow the number of profiles that are giving us VS30, and in blue the number of proxies giving us VS30 for all the sites in the database. And you can see about a third are profile-based and about 2/3 are from proxies. It's very uneven globally, so kudos to Taiwan and Japan. Okay, they're kind of the global leading folks when it comes to having profiles for their stations. We're still at about 17–18% in California, Western North America. We've actually added a lot of profiles. It's just that we keep adding stations at an even faster rate, and so our percentage remains low. All right, so isosurface depth was another parameter that we spent a lot of time on in this project. Just to give you an idea what it is, you have a VS versus depth profile right here, and we pick a value of velocity, a fairly large one, corresponding to firm conditions, and we find the depth to that, which we would call Z1. Prairie rock, and occasional fault-bounded basins that many of the cities are in over there. That's a very different geology. We might expect significant differences in site response over those small length scales. So how do we actually do this? Well, we calculate residuals, data minus model. We partition them into event terms and within event residuals. To show you the event term, this is a model for ground motion versus distance. An individual earthquake may be high. If we take the average through that earthquake, that is the event term for that event, which in this case is positive. Similar one is negative down here. Okay? We can similarly partition out side effects. So here's two sites, M and N. N is on the high side, so the side effect is stronger than the average, even with the VS30 included in the model, and M is smaller than average. So we can take those site terms and we can group them into different geologic units that we find in the San Francisco Bay Area. So this is an example of a sub-regional characterization. So we have what we call shelf deposits. These are relatively thin soils over that Franciscan rock west of the fault. And then we have basins in the lower left, and we have mountain hill areas on the right. And you see the trend lines. Basins have very strong long period site response. You see the values above 0. They have less than average at short period. These shelf deposits have different behaviors, but one thing they share in common is weaker than average long period responses. It's very valuable to capture these kinds of effects in our models. We can capture that effect through models that consider VS30 in depth, as it turns out in this case. The VS30 scaling doesn't need much change. But when we look at the depth, we don't look at the depth itself. We look at the depth relative to a mean for the VS30. That's because the VS30 itself is correlated with depth, and so we don't want to get into a correlation.
And I noticed I hadn't really worked in the ground motion modeling space before, but I've worked a lot in site response. There was sort of these new efforts in non-ergodic ground motion models, and I know there's talks about that later on if you're interested. And what the non-ergodic ground motion models are doing are they're trying to create these more site-specific estimate of path, but also of site. And there's 2 examples here from recent publications. The first one uses varying coefficient models, and the second one starts to adds in geology and interpolation, and is very similar to what I'm going to show you here. So these were motivators for me and inspiration in my group. And it tied to work that we had done about 15 years ago on developing regional site amplification maps. This is just an example from the Parkfield area. And we had done a lot of microzonation maps, and we had been interested in how you interpolate geotechnical data. And this is just an example there where we created a regional site amplification map using FPeak, the square root of impedance, the superficial geology, and VS30, so we could get, again, a map-based estimate of amplification. And one of the things that we found there, which people who work in this space realize is it's very hard to interpolate geotechnical data. The spatial correlation is quite limited, usually to 2 to 5 kilometers. And so you really do have to rely on superficial geology and other things to sort of get the full map coverage. And so, as you can see here, we have sort of 4 maps. One is I can also not read that, John, you're not alone. So one of those is FPeak, one is VS30, and those are interpolated only as long as the spatial correlation exists. So if you provide a map to someone, so the upper 2, they're not going to be able to apply that to their full infrastructure. And so the bottom 2 maps use geology and slope-based VS30 to predict site amplification, and then if you use a weighted average to combine those, you can end up with sort of a complete map. So this, again, was sort of inspiration for us as we joined the ground motion modeling community. So you have this choice. You can interpolate site data, or you can use geology and geospatial data to get to this map-based site. And I'll say that there's a lot going on in the interpolation space with the varying coefficient models, and that's really exciting work. But what I'm going to talk about is more in the second list, where we were trying to rely more on geology and geospatial data to get that map coverage. So the way we tend to approach this is we look at what proxies are available, and this is just an abbreviated list, and we try to gather ones that we think will tell us something about stiffness, topography, basin, and potentially saturation. And then you can see we need things that have full coverage. So in our, I'm just going to show you a quick example of sort of a proof of concept that we did for California, and then I'll show you some results from trying to embed this in the NGA West work. 3 work. So you can see on the right you have maps. So our we're conditioned on we want data that has that full map coverage. So in our proof of concept for California, and this is work by my PhD student Maggie Roberts, we looked at just California. We used the NGA West 3 data set wasn't available when we did this, so we used the prior design safe data set. She pulled off the residuals, which is what Jon had just talked about towards the end of his talk, to look at sort of the sub-regionalization or the spatial patterns in the site residuals. And when you look at that map, that's for 1 second, you can see that there are really distinct patterns in the site residuals. And for those of you who know California, those match sort of geologic patterns. And so we pull those out, and then we add back in the nonlinear and the Baise term, so we fit a model to the full amplification, the full site amplification term. And our approach is to have a geospatial term first. So essentially, we're sort of replacing, we want to first fit kind of the map-based site effect and basin effect. And then the idea is that then you could add back your measured data as a correction when you have site-specific data. And so we have our map-based term, and then we have site-specific terms. And I'm just going to show kind of the quick result. So on the left, wow, really, I'm going from memory here. The black, I think, is the black is the base model with VS30 and Z1.0. The blue lines, and this is the, you want something to be lower. Lower is good. We'll go with that. The blue is only using geospatial terms. And then geospatial terms meaning not geology. And then the red or the pink is showing when you add geology. So in California, it was very clear that the most benefit you got was the sub-regionalization that Jon was talking about earlier. So you add in geology, and you get a significant improvement in the standard deviations. And on the right, what I'm showing is that once you've done that, you get a map-based site amplification term. So for those of us in the regional space, this is really good for implementation. And so you would go, and even at site-specific, you would go with your latitude and longitude, you'd plug it in, and you pull off a site amplification term by period. So this was a proof of concept. Then we wanted to see if you added geotechnical data, if you could get an improvement. And we looked at both FPeak and measured VS30. And again, these are two different data sets because not every point has measured VS30 or an FPeak. So again, from memory, I believe the red line is the VS30 and the blue line is FPeak. And so you're looking at the improvement you get from the gray to the one below it. So in measured VS30, did I get that opposite? Can someone read it? Okay. So in measured VS30, you get the improvement at higher periods. FPeak, you get it a little bit across the way. So you still get an improvement with measured data, obviously, but you're starting with a better base model with the geospatial and the geology. So then we were invited to join this NGA West 3 project and sort of test this out over the larger region. And so the way we look at this is first we're looking for a geology, geomorphology based adjustment. Then we've developed a basin model that I'll talk to you about, and then finally a geotechnical adjustment. So with the geology-based model, we have two primary data sets. One is physiographic provinces, which are available across all of North America. Here I'm just showing them for the United States. These are sort of larger regions like the Basin and Range province. And so again, it's a sub-regionalization. And then for California, we have very detailed superficial geology, so we use both of those. Oh, I should say. And what that, the result of that is we end up with 116 subgroups across the area where each of those have at least 5 stations. So just to demonstrate this, taking 2 of those physiographic provinces. So the purple is the California Trough, and the green is the Sierra Nevada. And I think that says residual site term. So this is a test. You can see that those 2 distinct geomorphic provinces have different signatures in terms of the amplification, and that's what we're trying to capture. And then similarly, if we look at the geology, looking at two different sort of familiar regions, the first map is Los Angeles, and you have the blue is Mesozoic granite, and the red is Quaternary sediments, and the upper plot on the right sort of shows those differences. So again, you're getting a very clear signature in these two different geologies. And then the middle map is the San Francisco Bay Area, where the blue is Franciscan and the red is Quaternary sediments. And again, you're getting a signature. And those two signatures are different. So one thing that we've noticed is you can use just geology, but it's important to use both the geomorphology to get sort of the sub-region. San Francisco and LA are different, and then the geology on top of that. Okay, so then the second thing we looked at was a map-based basin term. So ground motion models use the Z1.0 that Jon talked about, but one of the issues with that is it's not generally available everywhere. And I should say, the everywhere, I'm from Massachusetts, things aren't available in Massachusetts. So I tend to be interested in things that could be available everywhere. So we developed a basin term using a wavelet transform that we applied to the elevation or the topography. Okay, so when you do that, you apply the wavelet transform across different length scales to the digital elevation maps. And then the figure sort of with the blue and red below is sort of showing the difference between what a basin would look like and what a non-basin would look like. You get a different signature in terms of the length scale of the wavelet. And then we can sort of look at small length scales, sort of around 3 kilometers, you would find a very low roughness because basins are relatively flat at the surface. And then at the longer length scale, you start to get sort of the edges of the basin. And so that sort of changes the length scale coefficient. So the two maps there, and we validated this first for California and Nevada because California is very well constrained. There's been a lot of work understanding the basins in California. And the two maps are showing a small length scale and a large length scale. And again, if you're familiar with the area, you can, again, start to recognize where you might expect to see basins across those different length scales. So when we apply that to the larger area for NGA West 3, we end up with these two key parameters. One is the probability of being in a basin, which is the first map. And the second is basin categories, which you can kind of think of somewhat as basin size, where you have non-basin, edge or transitional, small, medium, and large. And then, again, on the left, what you see is the signatures for those different sizes. So you get, and that's coming from the data. So we're looking at the observational signature based on whether you're in one size basin or another. And let's just assume the yellow one's the flat one. Yellow one's the edge. So the models fit so that the edge is the 0. And then you get, if you're flat, you get some de-amplification from the base model, and then in the other basins, you get amplification. And then if you fit this into a ground motion model, so these terms were developed sort of in partnership with the ground motion modeling.
Or support ergodic model, and that's in Harman et al. 2017 and Ilhan et al. 2020. In these simulations at the time that they were performed represented the largest set of simulations of 1D site response for a particular study in the millions of site response simulations, which is really record-breaking for us. It was all enabled because of great enhancements in computations and algorithms in nonlinear modeling in deep soil at the time. Now, we took that experience at the time, and in 2018, we did perform a smaller study for the Western US that encompassed only 30,000 simulations, but with a particular focus on, in addition to response spectrum space, we also looked at Fourier spectrum space. And that's where there's a lot of more effort now in NGA West 3 to work on. So that's where we started, and then this is the new parametric study tree that we have performed for the Western US, for NGA West 3. We had a larger family of ground motions, and this is the series of ground motions that we used, much larger than what we did in 2018, followed by a characterization of the soil profile, shear wave velocity profile, and I'll talk a little bit more about it using slowness as a metric to allow us to cover a broader space. And then we considered a series of types of typical soil columns. Again, even within a region like California, saying something typical does a disservice, and we're seeing here regionalization, sub-regionalization is very important, and I'm a big supporter of that. And then we add to that uncertainty around our stiffness profiles, our shear wave velocity profiles, and then we bring in some, this is based on data that was collected in the West, and then we also incorporate uncertainty in the nonlinear portion, the modulus reduction and damping curve, the nonlinear, the normalized modulus reduction and damping curve. But recognize that in nonlinear site response, it's the combination of shear wave velocity, modulus reduction and damping, and strength is what defines the full stress strain behavior of the soil that is then used in the calculation. None of these individually are used. It's actually just represents a singular curve. And then, of course, we end up with a family of these curves in our simulations. And we performed linear, equivalent linear, and nonlinear simulations. The linear simulations, we performed them because we wanted to define in our simulations what's the linear term and take it out from our nonlinear simulation. The equivalent linear simulations, we always like to have those to check our results in nonlinearity to understand the changes. But what we use is the nonlinear simulations in defining the nonlinear term. The improvement from Harmon et al. Is actually quite significant. I'm not expecting you to kind of understand all these graphs in detail. It gives you a sense that we have a far broader coverage of our space than what we've had before. This is in a draft paper that we'll be submitting soon on this topic. We have a total of 286,000 simulations compared to 30,000. Now you may say, well, why don't you have a few million ones like you had in NGA East? It was time and resources, okay? And we can also talk about these. We have a larger, of course, ground motion data set. We introduced the slowness term, inverse of VS, and we developed a slowness model, and allows us to have a much wider realizations than what we had in Harmon et al. 2018. Now, we take all of these, and then we press run, and we run these simulations, and we get data. It's as if you have now measured data. Of course, this is simulated data that we obtain from these large simulations, and then we go to develop model forms. And the simulation models are regressed to fit a particular mathematical function. As I mentioned, normally we use, or we conventionally use the response spectrum space, maybe a little bit about Fourier spectrum space, or Fourier amplitude space, but actually now we are working with effective amplitude spectrum, which is related to a Fourier amplitude spectrum space. And we had a series of models that we have, and we followed very much similar template to what we had for NGA East. We have a linear model based on VS30, and then we have a linear model based on VS30 and TNAT, the natural period of the soil column. And you'll hear me talk more about that in a little bit, why I put in TNAT there. And then we have the nonlinear models based on PGA and VS30, or EAS, and VS30 EAS at 5 hertz, kind of similar to thinking about a PGA. And then we have N2 models, peak spectral acceleration and EAS at a specific frequency, and of course, and with VS30. The nonlinear models, you regress nonlinear simulations minus linear simulations. Very simple way of thinking about the response we are dealing with. And that's what is then used in the GMMs. So the intensity measures that are used, as I mentioned, response spectrum is very commonly used, but we need to keep in mind that it does not represent the ground motion itself, but the response of a simple elastic 1D oscillator. And at short frequency, it mixes response at various periods, so it has its own limitations. A Fourier amplitude is a purest ground motion metric, if you want to think of it, about the amplitude of frequency component of the ground motion. Now, but it's one component at a time. And then the smooth effective spectrum introduced by Kotke Albert and colleagues in 2021, has both horizontal components there. So it's Fourier based, but it has the 2 component with a square root there. Why? It's direct representation of frequency content of the ground motion. It's orientation independent. It's compatible with RVT, so if you're trying to convert from FAS to RS, and that's currently work going on right now. And however, I should say, our site models, we directly develop them either in EAS space or response spectrum space. We don't do conversion because we have the data. We can process it in either space. So we don't lose fidelity that way, but it introduces other complications. So in terms of the nonlinear term we have is building on Shu Yang and then Sian and Stewart's work and our work with John and Alan Rathje on NGA East. And that's the model form that we're looking at, and this one is an EAS-based model and showing the performance of the model. The N2 models that we have developed seems to provide a better performance compared to our HEA model. We didn't spend time reprocessing the data from our 2018 simulations. We just moved forward since we cover better the space of interest. So now the standard deviation of EAS model residuals gives us an uncertainty. You need that uncertainty. Actually, John and Laurie both highlighted issues of uncertainty, and we carry it into the modeling space as well. It actually increases with, of course, EAS, meaning with increased nonlinearity, and it just becomes a challenge for us. And I'll elaborate more on that issue as well. Now, since we have this very large, fairly large uncertainty, and trying to separate, we're always trying to separate aleatory from epistemic uncertainty, I'm going to bring in some work we have done before on this issue and what's really moves the needle for our models. We found that when we did our work, we found some really interesting thing, and this is for NGA East, okay? And we haven't tested it yet on NGA West. But the natural period of the soil column with the VS30 causes a significant reduction in our standard deviation. So that's an important factor, and I think I'd like to see in the future, in addition to VS30 maps, TNAT maps across the country, if not across the world. The other one is actually model form itself. Even if I stay with VS30, and of course, we're in the age of AI, so we must mention something about AI. When we use, instead of conventional model forms for these AMP factors, we use artificial neural network-based models, so essentially they figure out the form. We also have a significant reduction in uncertainty. And so that actually is really, we showed tremendous improvement in performance there as well. Of course, you lose certain aspect or certain feel for parameters when you're dealing with conventional model forms, like I showed you earlier. But I think it's also promising when you're dealing with such large data sets, hundreds of thousands, if not millions of simulation. So I think the best way to reduce uncertainty is probably to introduce something, a combination of TNAT and ANN. So how's the model performing? And this is the nice thing about working together with the NGA West 3 teams, is that we looked at, actually we provided this to Norm Abramson's group, and they calculated within event residuals, and what they showed at the larger EAS, and notice the horizontal axis here is log scale, so you really are not seeing the strong nonlinear effects. It's also a little bit kind of crunched to the far left. What we see is that it reduces the bias, and hence it improves the performance of these models, showing that these models are doing a good job. We see the same thing if we do in response spectrum space. A little side note here on issues of, since we're interested in regionalization and incorporating geology, 3D variability is very important. And this work we're doing nowadays in collaboration with Brady Cox. And in order to build, by the way, 3D models, is to move away from 1D site response to 3D site response. And I'm not saying we're the pioneers. Many, many folks here have been working in that space. We are trying to attack it in a systematic way. Is to be able to build a 3D model, you need, the first thing is a 3D model of the velocity structure of your system that you're working with, all the space. So it's a non-trivial exercise. The other part is what is the maximum frequency you can deal with. The simulations that I'm showing you here is about 3 to 5. We're running ones right now in the range of 20-some hertz. So we want to see how it works, nonlinearity, how it performs, what's the effect of that cutoff frequency, because that's always been the Achilles heel of large-scale 3D simulations. This is Treasure Island Yerba Buena simulations that we have done, and this is based on recording, so these are low-intensity events. And we already see the significance of 3D effects. And what you're looking at are contour maps of the 3D over 1D. I'm assuming 3D is let's assume 3D is the correct, and 1D is the approximations we often use in our simulations. And what we did is we did 1D simulations at all these points. We just took the profile. It's not like we took 1D, 1 point, and used that for our ratio. We just went side by side or point by point where you have whatever the bedrock is for that. And we find that the highest 3D to 1D scaling factors are on basin edges. That shouldn't be a surprise. I mean, we've observed it, right? We've seen that. And we can see that in the simulations. The areas located on top shallow rock have the lowest 3D to 1D scaling factor. Long period show 3D to 1D scaling factors lower than 1. And these are linear simulations because they're near linear simulations. We are doing ones with high intensity events, strong events, and the results are currently being processed, and we're working on a paper on that. So that takes me to my conclusions. So approaches commonly used in site-specific settings can be used to inform ergodic GMMs and even regional GMMs. Simulation-based nonlinear site term reduces within event residuals for NGA West 2, and we're looking at both Fourier amplitude space as well as response spectrum space. There remains high sigma, high uncertainty, standard deviation in these models. We see the thing that moves the needle in the east is TNAT, and use a more elaborate model forms, ANN-based model forms. And I think it's something worth considering for the West. Three-dimensional effects can be important, and similar to what Laurie showed us about regional geology, I think this kind of complements it. And this is something we maybe we want to consider as we move to region-specific and non-ergodic models. And with that, thank you very much.
John. Thank you, Laurie. Thank you, Youssef. Do we have questions? Daniel has a mic. We have a mic next on this side.
I don't see anybody having a question, so I'll start maybe. Really, congratulations. This was a wonderful set of presentations. I remember during the Northridge earthquake in the area, for example, of downtown Santa Monica or along Olympic Boulevard, having basing edge effects or local effects. Can you comment on using these new techniques, how much this would improve on the state of practice? Thank you.
Yeah, so what you're referring to is, in that particular case, there was the earthquake underneath the San Fernando Valley, and the area you're talking about is a different basin, right? So this is San Fernando Valley Basin, this is a separate basin. So the waves are coming underneath the Santa Monica Mountains to the south, entering the basin through the base, and they undergo this process that we would call basin edge generated surface waves, right? So they come up, they come back down, there's a critical body wave reflection at the base, and they just keep going across the basin, and you end up with essentially love waves traveling across the basin. There is nothing in the VS30 or depth parameter that specifically accounts for that, right? So that mechanism for generating basin effects, as well as the mechanisms that occur in other areas, like, for example, lens-like structures and things of this sort, are not directly considered in any of these models unless you're doing a three-dimensional simulation. Where they are captured is in the observations that are used to generate the models in the first place, to varying degrees, obviously, right? So since we don't specifically parameterize that, and it's not like people haven't tried, it goes into the standard deviation, basically. So when we model the basin depth, when we look at VS30, and when we sub-regionalize, I think we get closer to it, but we're not yet to the point where, short of simulations, we can capture that specific basin edge generated surface wave mechanism.
Can I add, John? So I would say that we're not, so in the method that I showed where you have the geology and you're fitting the amplification functions directly to that location, you'll capture some more than you would with just a Z 1.0 because you're getting the observations from that location, but you're not getting the directionality. And so depending on, where the ground motions come, they may not all show the same basin. So at least theoretically, we're hoping that the sub-regionalization will capture some of it, and by fitting it not with simulations but with observations.
When you showed that map that showed Hayward and the bedrock, so I was expecting that it would have a really strong beneficial effect.
Yes. Yeah, I think it does. And so we haven't looked at every example, but because we're using the ground motions that were recorded in that unit, they should, and then we have, and then we also have the basin term that's also sort of capturing sort of whether you're in an edge or not. So it's not as good as a 3D simulation by any means, and you definitely don't have the directionality. But we think part of the reason why we're able to get a reduction in the standard deviation is because we're getting some of what was observed at that location, which is the same as all the non-ergodic models. Yep. So ours is an ergodic model that uses sort of place-based, map-based terms, so it captures some of it.
Thank you very much.
Yep. Maybe if I add a little bit on the simulation side. I think we could benefit from looking at the history of the last 20 years or so in the space of simulation. Thinking about when I started working in that, running these large-scale simulations of a few hundred thousands of millions was just simply out of question, simply because hardware, software, algorithms were not there. Nowadays, as intimidating as 3D might look like, it's actually not. And in fact, it's being used in practice in some projects. In fact, one of my good friends here has actually shown me some of the work he has done for a project where they did look at, because these effects were very strong because they have a situation of a underground structure transitioning from soft soils to rock. So we are, I think, in the potentially next 10 years or so, we'll see these becoming far more accessible, especially in terms of data acquisition, so that we can develop these models and then perform these simulations, and then coupling them with the reality, with the data.
Thank you. Yes.
Good morning. John, I have a question specifically for you, but I'd invite Youssef and Laurie. I'd be curious to hear your thoughts on this as well. And it pertains to topographic modification of ground motion or topographic effects. In the methodology you presented, you had a physiographic province or geomorphic province described as like hills, mountains. And I was curious as to why you were using that in lieu of relative position along a slope, something like analogous to what's done in Eurocode. And what's some of the thinking behind that?
Yeah, so, you know, if you think about what are the different processes that can affect site response, there's the classical ground response where the waves are just coming up through progressively softer layers, basin effects we talked about, and then topographic is kind of the third part of that problem. And what you were talking about in reference to Eurocode are procedures like you might say, well, I'm at the top of a hill, or I have a hill of a certain dimension, and things of this sort, which you can use essentially on a site-specific basis to try to modify the ground motion. Those effects are operating in generally at pretty high frequencies, so we're not talking about long period effects there. We don't usually include things like that in ground motion models. We leave that more to the domain of site-specific analysis. And the reason we do that is a very small percentage of our recordings, not zero, but a fairly small percentage of our recordings are in that, in a strong topographic condition. Now, of course, every recording has some topography. It's just that many of them are fairly flat, and even when they're in mountainous areas, they're usually not right on the tippy top of a ridge, right? And so it's very hard to unpack this at the level of ground motion modeling, and frankly, we don't even have those parameters in the database. Where that usually comes into the process of a hazard calculation is you would run your ground motion model, and then you would make adjustments for topography given the conditions at your site.
I'll add. In our basin term, it has the capacity to also look at the opposite. We've not done that in sort of an explicit way, but we're planning on it. And I would say that in our geology, geomorphology terms, the best improvement we have is the mountains, because we have observational data that's being fit to the geology. And that, sort of that location. And so we're getting a significant reduction in the uncertainty, and I think part of that is topographic. I mean, part of it is that we don't do a good job of their VS30. We're not measuring their stiffness very well, but I think maybe potentially we're also getting some of the topography effects. But our basin term right now does not have it, but it would be very easy to sort of use a wavelet transform in the opposite direction and do a better job on topography.
Go ahead, Joe. I had a question about site-specific information. So all of you touched on the fact that whether it's VS30, fundamental site period, or Z1.0, we don't have much data in the US. What is it going to take for us to get to a level comparable to Japan or Taiwan? And what can we do as a community to get us to that point that we actually have these pieces of data at these stations?
I can maybe take a first crack at that. So we have worked with a number of partners around the country, concentrated mostly in the western US, but some around the country, to assemble a database that has VS profiles, related metadata, CPTs, boring logs, and HVSR. So the short answer is whether it's that database or some other database, we need to collect the data that's already there. So that's part of it, right? If we were somehow able to mine the information that is in departments of building and safety and state geologist offices, geotechnical engineers do their work, they submit their report, and then it sits there. If we were able to mine that data, we would not be data poor, right? But that's been a logistical challenge. The other part of this thing is we seem to somehow have funding to deploy seismometers in different parts of the United States, but which is expensive, right? I mean, you deploy the seismometer, and it's not even the seismometer itself that's so expensive, it's the personnel that are going out to service it. That's very expensive. We don't measure the shear wave velocity profile or get these other parameters. So I think what the NGA East experience certainly showed us, and others, is that, you can get a lot of uncertainty reduction if you have these site parameters. You get more value out of the data you've already invested to create if you do this nominal additional work to create site parameters. So we've been singing that song a long time. I think we are making progress. It all depends on how you look at the data. If you plot the number of profiles with time, it looks like we're doing great. But if you look at the percentage of sites with site parameters, it doesn't look like we're doing so great, right? So it's something that we need to continue to focus on. It's not glamorous. You're not going to win awards for your papers going out and measuring site parameters, but you might make one of the biggest differences by doing so.
Thanks, Joe.
And I'll add, I think there has been a huge increase in the HVSR, and so to pick up on Youssef's, I also work in the central eastern U.S., and so we've been using sediment thickness as a site parameter in our work, and there is a national sediment thickness data set that is not very good. There's a very good one now in the Atlantic coastal plain. The map I showed of Massachusetts is a very good sediment thickness map for Massachusetts, and that was created by the state geologist. And so there has been an effort by state geologists. There is funding for state geologists to create bedrock thickness maps or depth to bedrock maps. So go to your state geologist and encourage them, to do it. It's hugely valuable, and I think that would be one of the big initiatives that I'd be interested in seeing is an improved national sediment thickness, the same as TNOT, but you can get it either with HVSR or with a geology-based sediment thickness map.
Yeah, like they said. For example, when we were working on the NGA East, the first version of our models, we had these proxy maps for VS30. And right now, we're just focused on, we have a project for state of Illinois, and we're trying to collect all their data so that we can actually have that higher resolution and improve these kind of proxy relationships, improve the overall estimates. But just the effort to find it, pull it together, and turn it into something meaningful you can work with is actually quite a bit. Because when you talk, people say, oh yeah, we have the data. Yes, well, it's kind of pretty dispersed. So, and now think of that on a national scale. It's a challenging effort, but it's needed. That's how we're going to reduce uncertainty.
Let me read you a question online. All this analysis seems to be leveraged on VS30. Are surface wave measurements good enough compared to downhole shear waves, or are they just used because you can get a lot of data cheaper?
So I'd be happy to take that question. The questioner is asking whether we use invasive methods where we drill a borehole or push a CPT and we're measuring shear wave arrivals down there versus if we only have surface instruments and we measure surface waves with those. That's the distinction. And different people are going to have different views on this. I'll give you my opinion. I see absolutely no problem with running surface wave tests, whether it's active source or passive, but there are certain things you need to look for. So one thing is when you do these surface wave tests, you're not measuring shear wave velocity. You're measuring dispersion curves, which are basically phase velocities versus frequency or wavelength. And so that information absolutely needs to be reported. You got to report what you're actually measuring. Then there is an inversion process to go from that to a shear wave velocity profile, which is highly non-unique. So if all you have no idea about the geology of your site, and all you have is a dispersion curve, you're going to get a whole lot of VS profiles, and there's going to be an unrealistically large scatter in the site response you would compute with them. If you can add something to the mix, and one of the easiest things to add to the mix is horizontal to vertical spectral ratios, show where the site period is, screen out all of the VS inverted profiles that don't produce a site period aligned with the measured one, you're going to get a much better result. That's a pretty low-cost addition to that site characterization campaign that will improve the reliability. And Brady Cox, David Teague, and others have really shown this quite nicely. So that would be good practice in my view. Let me give you an example of something that is bad practice. Passive methods, linear array. Just don't do it. You're going to have a high likelihood of a biased phase velocity, particularly at low frequencies. Passive methods, linear array. Two directions, you're fine. You don't want to use linear arrays. And this is unfortunately a very popular method in California, at least. I can't speak outside of here. So we have good and we have not so good, but we have opportunity to improve.
All right, question right here, yes.
Yeah, I just add to what John said. I think these surface methods are very useful when you're kind of looking at a larger scale type of studies. For project-specific studies, my personal opinion is, to the extent possible, have at least one or two invasive tests, whereby you do either a downhole or suspension logger or something like that, because the level of resolution you need is different there than, say, a broader study. You can complement that with surface waves, but I found that because of the uncertainties you're mentioning, and absolutely the work that Brady is contributing to and really leading has cleared up a lot of how you interpret it, but I think for project-specific, I don't see really a good alternative to this, either CPT, seismic cone, something where you go down and actually directly measure VS.
Question.
Yes, quick question. For the geospatial interpolation, that I'm going to call it, I saw there was some semi-variance with the number of observations. What type of kriging are you using? Some sort of kriging, exponential, ordinary, to create these maps? Because at the end, we're trying to reduce that standard deviation, right? Are we generating another set of a standard deviation there in that interpolation that we may need to take care at some point? That will be my first question. Yep. And then my second question is, when we look at the networks for NGA West 3, there is none on the Nazca plate, for example. Chile, I'm from Ecuador, so there's nothing there. Do you guys see any benefit at some point if those are added, for example, towards the Cascadian zone, which is a subduction zone, to any kind of advantage or benefit of having like a new network system on that area that can be added into NGA West, I don't know, 4, 5 at some point?
I'll answer the first question. So the semi-variograms I showed were for prior work in that Parkville example. In the work I showed here, there's no interpolation. So everything is categorical, so we have geology and geomorphology, which are polygons. So they're constants across those polygons. And then if we add a geospatial term, it's a continuous geospatial term that has a value at that spot. So there isn't any added, and that's sort of, by design. So there's no interpolation in this method I showed today. John, maybe you can answer the data set question.
Yeah, you were asking about, I guess, ground motion data sets in South America, Central America, things like that. Well, in Chile specifically, they've really increased the level of instrumentation. So like the Maui earthquake in 2010 was recorded by, I think, 34 records. At least that's the number that made it in to the NGA subduction database. So not that many, but we were sure grateful to have those. I think they've really increased the instrumentation. So this is one of those things that often happens after a devastating earthquake like that, is like the motivation goes up. Also, data sets that were, not sure what the right word is, almost privately held and not always released, are much more publicly available since that earthquake as well. So at least in the case of Chile, I think they're doing a lot better. I'm not too familiar with what's going on in Ecuador, Argentina, but you know, we had a short course yesterday on non-ergodic site response, which is doing all these things on a very site-specific basis. When you have these kinds of records, say at a dam site, at a power plant, the ability to reduce the uncertainty in your ground motion prediction is really considerable. So that alone may motivate increased instrumentation, at least for high-value infrastructure projects.
Any other questions? Looking at this side of the room as well, because I keep looking at this side. Oh, we have a question. Daniel.
Well, first off, I thought it was a very nice breadth of presentations that we go through measured data, modeling, geology, that covered it very nicely. One question I thought was for Jon was, and I'm sure you others have input as well, was, you know, I thought the graphics were really interesting to show the increase in data and measured data between the three different series of research projects. And, you know, the map shows California colored in red, but I'm sure that doesn't really represent the future advancement with, you know, of course, different types of earthquakes, I mean, especially Southern California. You know, since Northridge, we haven't had, you know, besides Ridgecrest, many big quakes. So how do you see the next set of data coming along with whether it's future earthquakes that are in our future, or just the increased number of stations, in terms of how that can help us, you know, on this goal?
Yeah, thanks for the question. So it is colored red. There are a lot of paths through California. Some of the areas that were a little sparse before have gotten better, like northeastern California. But it is, in a way, a little deceiving, because if you or someone who does seismic hazard analysis in California, you're going to have a very strong contribution in many areas from the San Andreas Fault. Magnitude 7.8 and higher earthquakes are controlling. You're going to have earthquakes on faults that are basically almost unsampled by that data set, and yet which are hazard controlling. And so it appears we're data rich. We're not necessarily data rich in the magnitude distance range that controls hazard using data from California. This is why we look far afield. This is why the data from Turkey, for example, is so valuable. It's the next best thing if you can't have data from your own place, right? So I think that is a data gap. Obviously, we're not exactly looking forward to that data gap being filled, because that would be a disaster for the state. But if it does happen, which we have no control over, we will try to learn from it. So that's one thing. I do think more instruments are going to continue to go in. I mean, the trend line is pretty clear. A lot of them are put in by seismologists to find sources and different things like that. But, you know, I know PG&E and others are instrumenting infrastructure, like I mentioned before. So I think we'll continue to see growth in these things. And, you know, one of the nice things about the folks who deploy these instruments is the overwhelming majority make that data publicly available, right? So there's this IRIS organization that assembles data and makes it available to the community so we can all benefit from it. So that's not a given, you know, and kudos to these organizations for making their data available.
Excellent. Any other questions for the panelists? Okay. can give the quiet, treatment that I do in class to get the questions out of the students. Do that as well in the attendees.
There is one more thing I might mention.
Sure.
This having a little more time to reflect on the original question about the basin effects. We would be remiss to not mention the very substantial efforts that are going on at the Statewide California Earthquake Center at Lawrence Berkeley Lab to perform, state-of-the-art, high-resolution simulations that do consider three-dimensional crustal structure, very complex representations of the fault. Whereas our ground motion models kind of indirectly, but don't specifically parameterize these sort of things like basin edge generated surface waves, these models do. And so one of the big challenges for us going forward is how can we better implement the lessons learned from these three-dimensional simulations and use them to improve our models. And so that's a really challenging topic. It's easy to say, it's not so easy to do. But it is one of these new frontiers that I think we'll see a lot of benefit from in the coming years.
Excellent. Youssef and Laurie, would you like any final remarks?
No, well, I guess yes, no. Thank you. I enjoyed sort of being part of this panel, sort of thinking about each of the pieces. And I think there are a lot of exciting innovations, really because of the data. The explosion of data has allowed us to look at ground motion and shaking in a much more high resolution way. And so that's sort of the benefit of these large projects.
Yeah, fantastic panel, and thank you for having me part of it. And as you can see, in the future is how we bring all of these pieces together so that we can come up with better, more reliable models. Our simulation capacities will continue to improve. Our data increases, however, gently, and our estimates related to issues of geology, et cetera, will improve. And when we bring all of that together, I think that's future, and that's why you see us work together too, as well. So, thank you.
Excellent. Let's thank our panelists. A couple of announcements before the break. Every attendee has the access to the full conference proceedings. Just pick up a card with instructions at the registration desk, or scan the QR code in the ASCE booth. PDH form, not PhD. PDH forms are also available at the registration desk. You'll receive an email 4 weeks after the conference where you can generate your certificate. I want to thank all the sponsors for the conference, for this Geo-Extreme 2025 conference. Don't forget to stop by the ASCE GI booth to get more information on ASCE and GI programs. Also at the GI booth, and I've already done this, don't forget to get your Ralph Peck bobblehead or get a retro logo t-shirt and other great stuff. And then last two things, there is a walking tour of downtown Long Beach. That starts at 5 p.m. and the meeting location is at the lobby. And then there are other things around downtown Long Beach in the Shoreline Village, all for free. Check in with the registration desk or with Brad for more information, get signed up. So with that, we have about a 30-minute break in the exhibit hall before we start our first technical session of the conference. And we'll see you there. Thanks so much. Technical sessions are downstairs. One less.